Share. So I posted Nichols' thing up, so we got that recorded. That's pretty good. Sorry I wasn't here. I had a funeral I had to go to. Anyway, I'm here now. Right. So we got this thing. Any questions on anything from Nichols' talk or anything? I kind of zipped through it, the YouTube of it. Yeah. Peak nanoseconds. Yeah. The time scale comes because the energy, like h nu, like frequency times Planck's constant as an energy. So you get neutrons of a certain, the temperature of the neutron, the kT, equals the frequency times Planck's constant. So the frequency and the energy are related to each other. And the energy has to do with this 1/2 mv squared of the neutron flying down a tube in a vacuum. So you can make neutrons in some kind of explosion, like a nuclear bomb or a nuclear reactor or the spallation thing, however you make it. And then they're going to fly out. So they're going to travel in a vacuum. They can travel pretty far. And then there's a frequency associated with that. There's an energy that you can convert to frequency. The frequency, you can Fourier transform that frequency spectrum to time. Like he does that in this paper. So he's got the, all right, so this is versus energy. So he shoots a beam. All right, so there's a lot to it, right? So maybe you can't get it all, but you can get kind of a flavor for kind of what's going on and where people cheat. That's kind of the main point, I think. But so you shoot the neutron as a particle, and it's going to fly. It's got wave and particle nature. So you can say 1/2 mv squared is energy. So it's got a velocity. Right? It's going down a tube. So if you got a spectrum of energies, the time of flight, so time times velocity is a distance. So you have some distance that it travels. Well, if the velocity changes, the time changes. So time's going to be the distance traveled divided by the velocity. So you can separate in time. If you detect at times, you can get different velocities. You have different velocities, you have different energies. And because it's also a wave, you can get the frequency or this frequency. That's how it works. The bar and the ones with the bar and ones without the bar. So they're getting this frequency. So let's see, I think this is the one. I don't remember which one's with the bar. Bar means 2 pi, like divided by 2 pi. So it's a RPM versus a hertz or something, I guess. So anyway, so you get this frequency. So you're gonna get an energy spectrum. So if you say you put in here a velocity selector, so it's like a wheel with these things that curve around, so they only let one velocity through. So if you spin this wheel, there's a pathway where it's spinning, and if the particle comes in, if it spins at the same speed as a particle, in other words, it will move over and the particle can get through, but other ones that aren't at that velocity won't go through that path. The things.
So the velocity is constant, right?
No, the velocity in the spallation, which both Nichols and this guy use, yeah, the velocity of one neutron is constant. Yeah. I mean, it's fine in a vacuum. I mean, it would slow down if it wasn't in a vacuum. So, and if you put it through a moderator, So they'll have in a reactor, they'll have water, they'll shoot the neutrons through the water and it moderates, so it gets rid of the super high energy ones that, I don't know what they do. Not good things. So you want the lower energy ones to do these measurements with. Then you get to the nanosecond time scale and everything. Right. So it's complicated, but basically there's a particle, because there's subatomic particles, there's particle wave duality to them, like an electron, a neutron, they can be a wave or a particle. And a photon doesn't have mass, but you can treat it like a particle. It's like quantum mechanics stuff. So it doesn't really matter, in other words, but basically in the context of the equations, it matters. So you can talk about it both in terms of wave and particle. You can do 1/2 mv squared. You do a time of flight, that's particle. Or you can say it's a wave and has a frequency, and the frequency is the energy, or 1/2 mv squared is the energy. And also, because they're a particle, there's a gravity effect. So they fly down the tube and they fall as they go because they have a mass. Right. So it's like not like, so with X-rays, they don't have mass, so you don't have to worry about the particles falling. Photons don't fall with gravity, but neutrons do. So there's a lot of problems with the time of flight. So you have the absorption coefficient changes with the energy. Okay, so because at certain energies, they can activate different materials. When they activate, they're absorbed. The neutron adds to the nucleus of something else. That's an absorption in this situation. So it's not with light, it absorbs and gives off heat because a photon doesn't have mass. So it just converts like 1/2 mv squared into, or see, it doesn't have mass, but it converts the kinetic energy into heat. No, you don't get it 1/2 mv squared like a hydrogen bomb problem with this. There's not enough high enough energy to do that. Right. So it does involve kind of nuclear physics. The whole thing is pretty much based on nuclear physics, which we don't know anything about, like basically a little bit, like we know it's not great sometimes, things like that. But so anyway, so the neutron, anyway, so yeah, it's particle and wave. That's kind of the point. So you can get, if you come in with one energy, and then it's going to interact with the material, and the interaction energy is like KT energy. So 1 millivolt, milli electron volt, MeV, right? So with X-rays, like 10 keV is the same as like 1.5 angstrom wavelength. So with a synchrotron, you're dealing with like 10 kilo electron volts, 10,000 electron volts. And here you're talking about 1 milli electron volt, which is significantly smaller. It's like 1,000th of an, so 1 million times smaller, right? In energy compared to the synchrotron X-ray, if you can compare them that way. So it's kind of, so this time scale of this thing is that, and the temperature is about KT. So if you have these hydroxyl groups, or here it's carboxyl groups interacting with lithium ions at KT energy. So the energy that would rip apart this is like del minus charge, and that's plus charge. So they associate. It's almost like a hydrogen bond with it. It's an ionic association. It's not fully a minus charge. It's like because a carboxyl can have the isomer, like that thing can flip over here. So you have another carbon, or it can flip here, and then you have a true minus charge, and that electron's ripped off, and that's floating back and forth all the time. So this thing has a partial negative charge to it. It would like to be negative, and because it would like to be negative, it associates with positive. So lithium can bond with it kind of on a time scale of, and he finds out in his paper, 1 nanosecond time scale, which matches up with this whole thing, the whole neutron energy scale, temperature scales, like room temperature. So everything's very nicely fits in with this measurement that he does. Right. So the question was, what was the question that you asked?
Time scale that you just mentioned.
Okay, so I guess I may have answered it, but it's kind of hard to tell. But anyway, you can use these velocity selectors to pick out a single wavelength. So they're mostly used if you have a nuclear reactor and you want one wavelength to come through for a scattering measurement. You want monochromatic for scattering. In this case, they're taking the polychromatic, and that thing's going to, because it interacts with this thing. So the neutron's flying in. I don't know, he's probably got a smiley face as he comes in. then he interacts, and the energy, the KT energy, it can shift this, it can slow its speed down by interacting with this, or it can increase the speed if it happens the other way. So it's like a Doppler effect, kind of. It's kind of like, but somehow it's not activating these things like an absorption. It's taking the energy of that bond. So the bond has an energy, it can deposit it into the neutron, and the neutron can fly out with a higher energy. In other words, it can speed up. And then, or the neutron can come in and remove the energy so it can slow down. So both things can happen. So the same thing can happen with light. It's called Raman spectroscopy. So you can come in with a photon, I don't know, whatever a photon symbol is, and then I just call it H nu usually. So the H nu particle comes in and interacts with a bond. So the energy of a photon is going to be similar to the vibrational energy of a bond, which is the same thing you measure in IR. In IR, you shoot the beam in, and the vibration of the bond absorbs the energy of the light, and that light disappears. Like you remove it, it's an absorption. Here, this is a scattering. You come in, the vibration of the bond can add to that H nu or remove from that H nu. So you get a broadening of the peak. Or you can get a broadening of the peak. That's his what is it called? Broadening of the peak is a phonon absorption that he was talking about. Or you can get it, or it can be quantized. So there's a fixed frequency that this bond vibrates, and then you get Raman, which would be like side peaks on it. A Stokes would be the subtracted one, and anti-Stokes would be the plus one. So the same thing is, it's similar to Raman scattering that you do in the shift. Or this is Brillian, Brillian, B-R-O-L-L, I can't spell it, I-O-N, it's like Boolean, like the soup, but it's Brillian, there's a U in it too. It's French, but I can't remember that spelling of the thing. Anyway, Brillian scattering is if you broaden the peak, and Raman scattering is kind of if you get the sub-Stokes and anti-Stokes peaks to it, right? So this is like this Brillian scattering, which Nichols has a machine to do that in his lab downstairs. He's so he kind of bought the machine that's a light analogy to this Quen's measurement. So he has both things that he can do. There isn't a big line of people waiting to do the Brilliant scattering, because it's similarly difficult to understand. Anyway, so we're expecting to see this broadening of the peak, which you can see. So it's a Doppler effect going on. Train coming, train going. The original peak is a black one, I guess. That's a resolution function. So there is some breadth to the original peak coming in. Like you're coming in with a beam, then you're scattering at a certain angle. That's associated with a size. So Q, 2 pi over Q gives you a size. That's the size scale of the scattering event that's going on, like the reflection kind of things, specular reflection. But there's also this Doppler effect going on, the train whistle. So it can go faster, it can go slower. So it can get a higher energy or a lower energy. And if it was a quantized event going on, so vibration of a bond, you would actually see a peak over here because it would be a single energy. Quantized means single value. So a bond vibration has a single energy value of plus or minus. And that can happen here too. So you can get this quantized event going on in neutrons too. That's mostly in metals. So it's not in soft matter. In soft matter, you see this kind of just gradual broadening, which you say is due to diffusion. Okay, so you say it's due to Brownian diffusion, random motion. Okay, which yields this equation. So it says that this is going to follow, this is a Gaussian. So it's a Gaussian in mean squared displacement, and it's also Gaussian in Q. So this thing looks just like Gounod's law. Like Gounod's law is Q squared RG squared over 3. And this is Q squared RD squared mean squared displacement by 6. So it's like half of the Gounod's law thing. Right. So, and it's in, the function is in, so the function is in like Q and T. So you could say, oh, I have a fixed time. So this is Gounod's law. Or you can say I have a fixed Q, which is the case here, and I have Brownian motion. This thing is for Brownian motion because it's cute. It's space squared is proportional to time somehow. Anyway, this equation is a result directly from Einstein's paper on Brownian motion in Q space somehow, you know. So this is quite a limited equation. You can only use it for diffusive motion, Brownian motion. Okay, which brings up the question, why the heck is he using this equation here? And the answer to that is because everybody else does. Because everyone at this machine, this backscatter machine, their software is all written to fit the data with this equation, which is for Brownian motion only. Right? So he takes these peaks and he fits them with that equation. And then he gets from that this parameter, the mean squared displacement, which should be the mean squared displacement should go with 2 times the diffusion coefficient times time. That's the Einstein's result from that paper we looked at a long time ago, the first paper, right? So this thing should go proportional to time. If it's Brownian motion, which is what the equation is for. Okay, so this is a good example of how entrained a technique and people can get and then overlook features that are like could be important to what they're doing. Right. And I think you'll run into this in other fields. Things are so complicated, no one, like people are walking into this, push that button, right? And you'll do this too. And everyone does that and it's okay. But once in a while you should stand back and say, what does that button do? Okay, like what exactly am I doing here? Right. So and this is a good example. So nature is the highest you can get for paper. So this has reached the peak of the thing. This guy, Bill Serra's a guy at Berkeley. He's a polymer guy at Berkeley. He does a lot of different stuff. So anyway, he's a nice enough guy, I guess. I don't like him. But basically, a lot of people like him. And then I think Wanatabe is a famous guy. I don't know. Oh, this guy's an Oak Ridge guy that does this machine. So he's a good guy. I mean, it's competent crew, you know. 2, I guess, is Oak Ridge, right? Material science. Oh, Berkeley. Maybe it's a different Lee. Is that 2? Or maybe he moved. This is probably a different Lee. There's a guy by that name at Oak Ridge too. And this is done at Oak Ridge. So anyway, so this is the main heavy hitter here, I guess, that got it into Nature. It's interesting. The other reason it's in Nature is this. So if you're going to do Nature, it's a follow-up paper to another paper by a guy that did NMR. Let's see, which I plopped here. I just put that in just now, but this would be a good thing to do too, but it's not really what we're studying. But so it's the same problem, but instead of using a $1 billion neutron scattering machine, they use a $100 million NMR. And they do this thing called 2D NMR where they get, so this is similar to the cross correlation thing we did with XPCS, so that you have 2 spectra, it's the same spectra. And then the cross one is where they're the same spectra, so you see peaks at it. So the peaks here, the cross one would be your normal NMR spectra, which would be kind of look like this if you blow it up. Normally it's like spikes because there's perfect quantized events going on. But if you blow those up, like look just at one of those spikes, then you'll see like these kind of features in it. You know, so this cross one is the middle one. And then when you see peaks off cross, that means that this vibration and that vibration are coupled together. In other words, the lithium vibration and the carboxyl vibration are the same vibration. So those 2 things are bonded. When that cross correlation disappears, then you know that stopped happening. So you don't have the cross links anymore. And then the thing can flow. Right. So he did that, and you can do that as a function of time with so you see the different times. You can do that as a function of time. You can do a lot of things with NMR. Most of them are too complicated to understand. The simple one is like you stick your sample in and you get a fingerprint. That's that stuff. Even that's a little bit complicated because you should be able to say, I have this molecule and exactly what the quantized features of it would be. So I know exactly what the thing is 1-to-1, like a fingerprinting. But basically as an understanding, as a map of the whole thing. Then this is like studying dynamics with NMR, which you can do by, because you're looking at the nuclei and they have a nuclear spin which precesses, and you can pulse it with a magnet to make it move, and then you can watch it decay back to how it was wiggling before under the field. The whole thing is under a giant magnetic field, and you pulse it with a radio wave to make it wiggle. And then you can watch how it decays, so you can get that decay time, which is kind of these taus. So you can look at this cross correlation pattern, which is somewhat similar to XPCS thing, and then do it at different times by pulsing it in different ways. And then you can kind of watch at what time scale does that lithium carboxyl group fall apart, which is exactly the same thing as trying to do with the quins. So the two things are coupled, and they both involve nuclei and neutrons, kind of nuclear spins. So the two fields are kind of parallel but grew separately. So they'll use the same kind of ideas, and there's some cross between them, like using the spin, control the spins in a neutron scattering measurement too. So you can see this can get really complicated, right? So, but you can hopefully get kind of a little rough idea what's going on a little bit, and maybe how the two fit together. Anyway, this was published in JACS, which is like second tier to Nature and Science. So you have Nature Science, then JACS, and proceeds in the National Academy of Science, the US, if that's going to exist after Trump. Basically, you never know. These things could have a very limited lifetime now, but JACS should maybe still exist, supported by the oil petrochemical industry, I guess. But anyway, who knows what the world's going to bring. But so anyway, this thing is worth reading in its own right because of this field, the NMR field, just to give a feel of it, of what you can do with it, which is a lot. And also the nice thing about NMR is if you're an analytic leaning person, and someone's going to buy $100 million instrument, and they're only going to pay you you're going to cost maybe $1 million a year for all your fun things you play around with. And then you're going to support a bunch of people with this $100 million, maybe $200 million instrument that has a lifetime of maybe like 8 years. So they're going to have to shell another 200 million in 8 years. It means like you have a guaranteed job. You're going to work in a dark room in the basement because it has to be like a solid footing and everything, but you have a lifetime employment anywhere in the world. Any place that can afford a $100 million NMR, and it's used in medical, which means like as any hospital, like every place is going to want to do these. And the technique of it is also the basis for MRI, magnetic resonance imaging too, which is used in materials and in the others. So it's not a bad thing to do if you can stomach like nuclear physics. You have to kind of understand a little bit about what's going on. So quite a few people do that. I mean, and if you can do quite a bit with it. It's a field that's been around some time at this point, but still has a lot to contribute, like this business. So anyway, that's a pitch for NMR. I don't do it. So, but anyway, it's definitely worth looking at as a career option. There's a good NMR lab at UC in chemistry. If you want to kind of play around with stuff, they can do these experiments there, like what they did here. And there are some permanent people there like that I'm talking about. And so anyway, so that's kind of where the base. So it's published in JACS. That makes it kind of relevant enough to go to Nature. And then since it has this guy on it who's bigger than the JACS people, then it makes it to Nature, and Kachunk it's in there. So this is like a 20 citation index 20 or 30 journal. So it's pretty high. That's good. And JACS is maybe like 20, I guess. Well, it's kind of considered second tier to these. I don't know why, but anyway, so we got a series out of here. All right, so he's talking about solvation. So you have a lithium ion battery, right? So you have an anode and a cathode. The cathode's made of this cobalt, which comes from coltan from Congo, where they have child labor making it and stuff. So they want to get rid of the cathode. I think Eero's doing some work with cathode stuff. And then the anode's a real problem. It's lithium, and it can make dendrites that reach across the battery and short it out. So the anode is where the death of the battery comes from, and the explosion stuff. Because once it makes a dendrite, short circuits, then it heats up and then it blows up. And the electrolyte is this phosphorus, nasty killer chemical liquid. So once it heats up and blows up, then the oozy stuff that comes out kills everybody. So not only is there a heat explosion on the airplane, then also like the liquid that comes out is extremely toxic and corrosive, right? So not good for being in an airplane with lithium ion batteries. It's not a good thing at all. So you use a way around it. You could make a solid electrolyte, like a polymer electrolyte, but the transport in liquid and polymer are different. You know, it's much faster in liquid than in polymer. You can also make a ceramic solid state electrolyte that's not subject to dendrites and doesn't ooze out poison chemicals. So the idea is like you're going to swap out all the liquid electrolytes with these solid electrolytes, and then the world will be a better place somehow. You know, I mean, basically, he also claims that these solid electrolytes are going to boost the power of the battery. I'm not sure how that works, because the chemistry, the action where you get the power is really at the cathode and the anode. So if you increase the lithium storage capacity of the anode with something like silicon, you can increase the battery density, energy to density ratio by a factor of 20. So it means you would have a battery, the same battery you have in a car now, except you'd only have to charge it once a year. Be like an oil change, right? So it's possible, and that exists. There's technical issues, engineering issues to developing that, and that's only one. So the answers to the battery already exist. It's just engineering to make it happen. And then you'll have like, you'll have like people complain about gas cars. You know, people complain they have to charge an electric car all the time or something. But actually, if you never had to charge it, basically maybe once a year, once every 2 years, right? I mean, that would be like pretty incredible. I mean, also for devices and things. So anyway, there's a lot in batteries it's worth kind of looking at. But so they're looking at it. And then one of them is they claim that swapping out the electrolyte with a solid electrolyte can boost the power somehow. I don't really get the thing about that. Anyway, so they're looking at what they call solvation in the case of where they have a polymer and a lithium ion. So lithium ion's carrying the material back and forth. Solvation by the polymer, and they're going to measure it in terms of these time scales of association with this carboxyl groups on this polymer they're using. So they're actually using kind of oligomers of this guy. So you can see it's got this ether group and then some carbons, right? So it's hydrogens that are missing here. And then, so the normal solid electrolyte is PEO, which is oxygen, carbon, carbon, ethylene, 2 carbons, another oxygen. So this is kind of like a PEO-like thing. And what PEO does is it's going to make kind of a crown ether structure. The crown ethers are these PEO-like things like carbon, carbon, hydrogen, carbon, carbon, oxygen, carbon, carbon, oxygen. So it's an ether, then a metal stuck in the middle. It's like ferrocene. Ferrocene's one that you may have run into. So you put an iron in the middle of that. So that's an additive for diesel fuel and stuff. It makes the engine run better because it somehow prevents carbon buildup in the exhaust. It kind of makes an iron catalyst when you burn the diesel, this dissolves, and if it's iron, dissolves in diesel, and then when it burns, it makes iron ions that are catalytic to burning off the rest of the carbon. It's kind of a handy thing to throw into diesel fuel. But it's also, you can do other things with ferrocene. It's a crown ether. Anyway, so this is like PEO. So when you stick lithium into PEO, the PEO chain is going to make like a little crown around it, kind of, right? And it can be multiple chains that associate with it. So that's kind of the standard bearer for this solid state electrolyte, because PEO is cheap too. It's in like hand sanitizer and stuff. It's in when you need to do a colonoscopy and you drink this Jello stuff or like Kool-Aid or whatever. PEO is polyethylene oxide, so it's or it's also called PEG. It's the same thing, yeah. So it's basically this carbon. It's like one of the more popular things in research, you know. So you have hydrogen, hydrogen, oxygen, and that just goes on. You just have this is an ether. Right, the oxygen carbon link. Yeah, it's PEG. It's PEO. It's hand sanitizer. Hand sanitizer is CCCO to some N and then CCO to some M. So this part's not water soluble, that is, so it makes a gel. And it can mix with ethanol. So hand sanitizer has ethanol, not propanol in it, because propanol doesn't work. So basically, theoretically, you can make a cocktail with hand sanitizer, but if you're inclined to do that. I'm not sure why hobos don't do that, but maybe they do. They may do it, I don't know, but basically you could eat it and get drunk and it wouldn't kill you. I don't recommend it. Just don't do that. But basically, all right, so let's see. So anyway, this thing has that kind of structure, but here they've inserted these, this is called PPM. It's got a long name. I don't remember what it is. Basically, the two carboxyls. So saying these ethers don't have anything to do with it, even though it's the main action. And so this is a much more electronegative because of that resonance structure where the double bond can flip. So that these are much more electronegative than the ethers, which ethers just have a draw. The carbon draws, or the carbon donates electrons to this oxygen. So it's just like a kind of a donation thing. It isn't a resonance. So these are stronger, so these dominate I guess, the thing. And then they say, well, if I get enough lithium ions in there, so if there's not enough lithiums, it's only going to bond to one chain. And then if I get enough lithiums in there, then it'll bond to multiple chains, and I get cross-links forming. And then that's what freezes up the lithium transport. So that's called that is called, what is that called? Sticky Rouse behavior. So Rouse behavior is, you have this chain, it's a bead and spring chain, and it's going to kind of vibrate into modes. So the way this ends up is that it's going to be like a guitar string that's got different modes of vibration. So if you ever play guitar, you can get an overtone if you put your finger on the highest whatever, and you pluck it, it goes, if you just string it, goes, and that is like multiple modes of vibration, not just one. So the guitar strings go on like this. So it's got, you have the string, it's fixed by these two things. It's got the basic tone, like the E string. And there's these other overtones. It's like one like that. So this is N equals 1, N equals 2. You could do like N equals 3. You can do N equals however many. So if you put your finger like right on one of these nodes, and you get this higher pitched tone. And if you just string it, you get all those tones. But the tone that has the highest energy is the N equals 1. And for a polymer chain, it's made up of beads and springs. So each bead is going to have a friction factor that's 6 pi viscosity times the hydrodynamic radius of the bead, and the hydrodynamic radius of the bead is NL squared, or n to the 1/2 L, right? And then the spring constant is going to be kT over NL squared, or 3 kT over NL squared. So we take our things and put them in the spring constant and the drag coefficient. Then you can say the force is the velocity times the drag coefficient, right? And then the force is also the spring constant times the position. So this is dx dt, and that's x times the spring constant, which is that number, 3 kT over NL squared. Then you add in like some kind of a kick, like a thermal kick that makes it kind of vibrate. So this is kind of your kT energy going into it. And then it's a differential equation, dx dt, and then x, and you can solve it for the position of the particles, and you can get all the properties of the motion of it, which ends up being a guitar string. So the mode that you're looking at is N equals 1, and then from that, the time of relaxation for that, which is called the Rouse time, is going to be proportional to the molecular weight squared in the end. You can get all this from ChatGPT, by the way. It explains it very well if you need to know. It's like better than anything, Wikipedia or whatever. And the good thing about ChatGPT is you can ask it questions like, that doesn't make sense to me. Can you explain that better? Or isn't it supposed to be like this? It's actually pretty good. I'm starting to really like it, but more and more, it's my best friend. So, anyway, so all right, so what do we got? So solvation, he's talking about, he's got these time scales. That's the Rouse time scale, which was for these vibrations, internal vibrations. So if you look at, so what happens if you look at different times of this thing? So let me just skip to the, let's see, let's skip to the here. So he's got, this is the thing. So he's, all right, so he's using, all right, this is, there's a lot of strange things going on here. So he's got this equation, which, okay, so if you're looking at that equation, so just, the beginner's mind, the Buddhist thing, right? So it's like this. You take the equation. I've never seen this before. So I'm saying, and you're saying that I should believe, or Einstein said that S of QT equals exponential minus, what did I just say? Minus Q squared, then this root mean squared displacement divided by 6, that would be Guinier's law, like Q squared RG squared over 3 would be Guinier's law. And then got R squared displacement as a function of time. So you've got the time component and the Q component here. The space component looks like Guinier's law, which should show like log I, log Q. It should show like that, like a knee, right? So anyway, so the time component of that thing is a Gaussian, so it's going to be a bell-shaped curve like that in time. It should be like that. So in the kind of the depth of this thing, the width of it is going to be something related to this RD squared T somehow. So you can get that number out of the data if you can convert it to time. He has a S of QT as a function of frequency. So he does a inverse Fourier transform, which is the same thing as the Fourier transform, except it's like 1 over 2 pi instead of 2 pi. So you can do Fourier transform forward and backward. They call it inverse Fourier transform. So you can convert the frequency to the time domain. And they do that through a software. They just say what software they use. Then they get this, then they fit that equation to this equation, which assumes Gaussian, assumes Brownian, assumes diffusion, right? Because it's R squared, so it's basically, it assumes that R squared of T is proportional to T. That's Brownian. So R is going to be proportional to the square root of T. That's a signature of diffusion, right? So first off, you should be plotting SQ of T. I mean, it should be, anyway, you should be plotting that equation, that thing's going to be the 2 times the diffusion constant times time. That's Brownian motion. You should probably think of plotting that thing versus time would be the plot. But all right, so he goes to Rouse motion, which predicts that R squared of T is going to go with T to the 1/2. That's Rouse. So diffusion that's proportional to T. And then this thing about sticky Rouse, which is a model people have come up with in the past 7 or 8 years, says that this thing should go with T to the 1/4 if you have these sticking things like crosslinks, like lithium crosslinking, if you get the 1/4 plot. So he says he has a Rouse parameter, R squared T divided by T to the 1/2, which should be constant. So it's constant for Rouse. If you have the sticky Rouse, then it should kind of look like that with time. Because let's see, for constant, I think it should come down with time. And then once you get to Rouse, when it goes to T, it should go up because this is a stronger dependence on time and that's a weaker dependence. So weaker means it drops, stronger means it goes up. This is the beginning of Rouse. That's the end of Rouse. Right, so this would end of Rouse means the longest time, which is the longest vibration, which is a Rouse relaxation time, the time for the guitar string to have the tone, the big tone, the full string shaking. Right, so that's the idea. So he's got these times, and then he does this measurement. All right, so you can see this. Hopefully, you can see this a complete flaw to this thing because the function he's using to get his R squared of D relies on diffusion. Relies on T, not T to the 1/2, not T to the 1/4. And then he's going to reduce it with T to the 1/2. So he's gone off into like never land. But this is standard practice in this field. Okay, so you can't really blame Balsera for this exactly. Although you can, I do, but basically you can't, if you reviewed this paper for Nature, because he'll just say, look, everyone else did this. Look at all these other Nature papers, right? And then you can't really argue against that with facts, right? So this is the problem, an issue with science, that it's based on this kind of Joe Schmo did this, he's famous, so it must be right, right? So this is a kind of a pretty decent case of that. Then they run to this problems.
And they don't argue a big name.
They don't what?
They don't argue a big name.
Right, yeah, a big name. Why would you argue? Because you're trying to get money for grants and you're trying to excel in your career. And if the big name guy writes a review and says he likes your paper or he likes you or whatever, then that's how you get ahead. And everyone's trying to get ahead. So it's kind of a catch-22. If you go after the big name, then you're trash and you're nobody, and no one will listen to what you said anyway. Or you could just go along with it and like say, that's how it is, and then just everyone's happy. But the problem is the truth is lost in that process, right? So you run into problems like this, like when you go to plot it, this thing isn't work, like this shouldn't exist. It has to go down, right? So he has to have this drop. That's his t to the 1/4 power, because it's a weaker dependence than the t to 1/2 that he's plotting. T to the 1/2 is there, which means it's subdiffusive, even though he's used a function that assumes diffusive to get it. And then he gets diffusive at the end, like it goes up. It doesn't exactly reach t, but it kind of goes up. And he says, well, getting t, you'd have to go to like 5,000 nanoseconds or 5 milliseconds. So maybe you'd have to use XPCS to get that, which measures milliseconds, right? So anyway, so he does get a flat thing, which is nice, I guess, with a data that doesn't mean anything, right? So now this plot is really interesting. Okay, so I think I said at the beginning, I hate to rip everything apart, but basically, and I looked at this paper and I thought it was short and pretty easy and it wasn't going to be a problem. And maybe I'm skeptical in my old age, but basically, I think I said, yeah, I said here. So if you have this function, right? So what would you do with that function? So here, and what would be the first thing that you would do with it? So you have S of QT, you want to linearize it in time, right? So you have exponential minus Q squared, and then this R squared T thing over 6. So you naturally want to get rid of the exponential, so you take ln of S of QT. That would be the first thing you do. And I asked ChatGPT this, and it said, yeah, you're right. So, and it also explained like why people are doing that other thing. Then you get that, and you could have this versus that. Then it says like this thing is generally not an exponential, but like a stretched exponential. So it has a beta here, and then basically because of that, people go to this plot. So it gave some really wishy-washy explanation for like why, and he doesn't give any explanation, but the standard to plot instead of log of S of Q versus log of time, which would imply that time goes with the exponential of S of Q, which doesn't make any sense. Like that's insanity. This is a plot that says that you should exponential your scattering to get the time. It doesn't, it's stupid. It's like a really stupid plot. And they argue that the reason they do this is because you have to consider different time scales, and you wouldn't be able to see the small time scales if you didn't use a log scale on this. So, I mean, that isn't how you do things, And then also, and there's other functions you could use, like 1 over time would do the same thing. And that might have some meaning, but anyway, then they say also because you plot it this way, it can bring out like that there's 2 regimes here, even though there's no meaning to the straight lines. That's why he doesn't draw straight lines in here, because that would go beyond the realm of just using it as a visual, quote unquote, visual guide. But the visual guide the way you think about things, so it isn't just a visual guide to use a plot. the plot has to mean something or else you're lying. You know, like I can plot, I mean, an example is like you can do a Lorentzian plot, intensity Q squared versus Q to something that doesn't have a peak, and it can make peaks appear. And then you can start saying that that peak means something, like the breadth of that peak means something. But if you have a scaling transition like 2 to 1, and you plot it IQ squared versus Q, you'll get a peak. It has no meaning, you know. It's just something that's invented from the plot. So doing random plots, it's okay as long as you can argue why it's log of time. I mean, it's a good way. I'd suggest like trying every possible kind of plot and see if you get linear. That's a good approach to take. But once you find the linear, you have to explain why. Like that's the whole point of it. Just saying I get linear and that means the transition is worse than lying about something, you know. It's like basically that transition doesn't exist. It's the plot that generated it. So here, that's what he's saying here. There's a transition, and it's, I think he even says it's a guide to the eye, something like that. So this is a big problem, that plot, but it's common to do in this field. So he's just plugging in at the machine what they have. Anyway, so he's got these times from this. He's got the one here, and then he does a computer simulation using a software, not lamps, but he's using Bromax. He's using this Bromax software, which is something like lamps. It's also free. I think they say like free and open, right? So you can download it. Bromax is kind of for biology. It's kind of where you need to put water into your system, and lamps isn't designed for biology exactly. It's more like materials. So anyway, you can use Gromax. There's a web page for it. He's using that because it's got kind of these ionic bonds going on. And I think it handles it better. So he does a computer simulation. He gets this thing, and he's got all the signatures that he sees in his measurement, basically. Everything that he sees here, the plateau, the rise to diffusive behavior at the high end, the drop at the beginning, that's the subdiffusion due to the association. So the T to the 1/4 power, T to the 1/2 power, then going towards T to the 1. But he doesn't see this ditty, like this weird thing where it's rising up, which would be below the first Rouse time, below the association of the ions with the polymer. Then you see diffusive motion of what? Like of nothing. Nothing's diffusing at that time scale. It's too fast. It's too small of a time. So this doesn't exist. This is probably a manifestation of that the function he's using to model subdiffusive behavior is only appropriate when you're looking at diffusive behavior. By definition, it was written by Einstein. You know, it's like, it's totally screwed up, right? So instead of saying like, we're making this all up, he says like, we don't know why that happens. It's interesting for future work or something, you know? So anyway, I'm not saying it's a bad paper, you know, but basically, there seems to be problems. He relates, so he can calculate the Rouse time. He compares it with this T2, which is where the Rouse time begins, and they match. They match perfectly. I mean, I'd call that perfectly. And he does the same thing for T1 and the onset of this ion formation. We can calculate with the energy of association or something between lithium and the carboxyls. So they match perfectly too. So this is pretty nice that they match up. And then he gets that tau S, the tau of solvation, the thing he's comparing with T1 by doing a probability from the simulations of a lithium ion bonding with the carboxyls. You can calculate, all right, and the reason why the simulation doesn't show that thing is because he's not using, in the simulation, how do you get this R squared from the simulation? Well, you know where the position of every atom is in the simulation, then you calculate the position of the atoms as a function of time. You don't use this function to get that. You just take the position minus the mean position, square it, and then plot that as a function of time, and you get that function. You just sum up over all the atoms in the system, right? So they aren't using that equation. It's strictly Gaussian. So then they get the behavior you'd expect from it, right? So that's why the two things, in my opinion, why they don't work. It doesn't work for the experiment because he's using a function that doesn't make any sense. You know, so he should have used something else. One example So the traditional way to deal with what's called a stretched exponential, the reason, all right, so traditional way to deal with one traditional way is this, what's called a Vrami equation. So I put that in here too. So there's a lot of little chunk things here. So it's basically, this comes from crystallization behavior where you get a stretched exponential in the end, and the exponential has to do with the dimension of the growth of the stuff. So you end up with, like, you can do this with a microscope and watch spherulites grow, things like that, crystals grow, or different shaped crystals. It was invented by metallurgists and was adopted by Polymer because it's easier to view this stuff in polymers, crystal growth. It's on micron scale. You can see it on a microscope. And they tend to grow in fibers or sheets. So you get this dimensional analysis. So the Avrami thing is this double log plot. So you have log. So you have an exponential, and the argument exponential is to a power. So you have to take log to remove the exponential, and you take a second log to get rid of to remove the power, versus log at time, because you're doing this time to the power. And then the slope is going to be what's called the Avrami exponent. It would be the stretched exponential exponent. So it's a double log plot. The problem with this is that everything looks linear in a log plot, and everything looks linear in a log plot. Log plot, so it's kind of like, yeah, it's linear, look at that, it worked, and the slope means something. So there is a problem with looking at stretched exponentials like that, but basically the Avrami is something that could come up on a qualifier question or something. Like you should know the Avrami somehow. It's kind of a materials thing, like it's crystal growth, but basically it's something that's useful to look at stretched exponentials with. Anyway, I think that's like a long time ago. I don't know when Avrami was. Oh, 1937. So it's not that long. I was thinking 1800s, but anyway, what time? All right, so I think that's a lot of the stuff here. Isn't there anything else? There's a lot to it. I didn't even mention the other paper, but I think that Nichols may have talked about the other stuff. Sticker lifetime. So he gets a sticker lifetime that matches with the NMR. No, a sticker lifetime would be the lithium carboxyl lifetime. And then that's most of the stuff. In the calculation of the Rouse time, that's basically molecular weight squared. It goes with the Rouse time. And then the supplemental, he goes through molecular weight dependence of this stuff. Some of this you have to, like the GROMACs and things, you have to look through the supplemental to find. It's a pretty good paper. It's just like the field has problems. He's just taken what the instrument scientist told him to do and he did it, but it didn't really apply to this. It sounds like it doesn't apply to most of the things people are doing. So it's kind of like people are just skipping over the details and then they run into problems after. Anyway, so I go through a thing. So I have like a bunch of slides on the Rouse model. The funny thing about the Rouse model is that it's based, and it never was noted that it's based on this. I got to fix that. Oh, that's too bad. So it's based on this. It's based on the Debye model exactly. Like so, the Debye model for heat capacity, which is in this class. I'll put it in the right links. I didn't check the links, I guess, when I did that. So if you go here, and I said what the slides 33 to 77 here. Sorry. Go down here. Let's see. So the reason I bring this up is because Rouse didn't cite it in his paper that he wrote at University of Illinois for his PhD thesis, which is the basis of this thing. So this is the Debye model. So it should look familiar to you. It's a Beeden spring model, and from this he gets the relaxation time. He gets exactly the same thing that Rouse got, the guitar string thing, that there's a maximum mode to the vibrations. He does exactly the same analysis. And he comes up with the heat capacity, the Debye temperature that gives you the heat capacity. And Rouse had to take this in an advanced thermal class. Everyone that's taken an advanced thermal class, this is the main topic. So, right, so basically, he had to have taken this, even in chemical engineering. He was a chemical engineer, Ralph. So basically, anyway, so Rouse never noted that he took Debye's model exactly, almost verbatim, and stuffed in the polymer drag coefficient and the polymer spring coefficient for the springs and the drag. And then he got the Rouse viscosity predictions and diffusion predictions, right? And then that became the basis for everything else, including the reptation model and everything else. In fact, nobody has ever really cited that it's exactly this stuff. And this was done in 1913. And the Rouse stuff, I can mention in the notes, it's worth mentioning that. So 1912, 1953, so 40 years later, right? And they don't even mention that it's from a textbook. I mean, it's kind of crazy that, you know, it shows you that it's complicated and people didn't really, maybe people didn't, I don't know how that happens, you know, how you can steal something exactly and paste it in and just say it's like something new. But there it is. There's probably many examples of that. And then anyway, let's see. So the timescales, I kind of went through them, most of them, I think all of them maybe. So it's just like go through like list, like this paper is about timescales. It's about what happens when you put a lithium ion into a polymer electrolyte. Then there's all these motions are going on, and there's short time scales and the longer and longer time scales, and finally the polymer diffuses, right? So basically he's breaking apart the system into time scales because he's got a machine that can measure time scales. So, you know, NMR does it too. Someone else did it with that. And then Fourier transform, blah, 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 subsequently. So that's our squared thing is one way to do this. And another way, I have 2 minutes. Another way to do it is what Nichols talked about. And it's in this, so there's a lot of papers in this field, you know. Let's see, Neubauer, it must be like, where'd it go? That's Chromax. I just did it and it kind of, I didn't look where it went. Open a new tab. Oh, it's, wait, is it here? It's this one. So he's doing exactly what I think Nichols may have talked about this, but you can take this S of QT and you can divide it by the Zusammensumme, the partition function. So it's an energy, it's like a quantum energy thing. So it's quantum energy dynamics. So you can, this NB is this how the sum of the energies. So it's going to be N times that energy summed up over all possible energies in the system. And the sum of N going from 0 to infinity ends up, that's the infinite power series thing, because N times that is that to the power. So it ends up to the power series is just 1 over that thing minus 1. The infinite geometric series is 1 over the thing minus. So that's just the sum of all the energies. So you take your thing divided by this function in H nu, and then you can convert that from the scattering to the what's called the susceptibility, which is like the ability of the system to interact with a magnetic field, like how much it interacts. So it's complicated. Anyway, that thing, because it's like an interaction versus a scattering function, that follows like Gaussian peaks. Like in other words, the contributions to that thing are peaks, and you can fit that curve with a bunch of Gaussian peaks. And then you can say like the contributions of the different kinds of times, the different times associated with what you're looking at contribute to that to a different extent. So you can say the distribution of things that are vibrations that are happening in the system, or whatever motion diffusion is happening. So it's a different way to analyze. It's the same data. You can see it's the same data, the peak, the broadening. Did he talk about susceptibility, or he should have mentioned it, but basically it's a different way to do it. This doesn't depend on assuming that it's Brownian motion. That's one advantage of this. So it's basically looking exactly at the spectrum of what's happening. Like these are the peaks. You can figure out what the peaks are. Problem is it's like a messy fit to the thing, right? So, all right, so we're out of time. One of the questions is like compare the two, but don't worry too much about the details, but try to get some feel. If there's 2 methods to analyze that data, it's the same thing. So it's the same data. Anyway, we got to quit here. So anyway, it's a lot. So just try to email me and try to get, something out of this. It's complicated, but hopefully you learn something kind of working through it. So. Feeling.